Okay, so yeah, from now on, I want to use this Substack um, app for at least for informal communication for affiliate program. So there is no Google form anymore that I used for registering or that you where you could register for this affiliate program. I will just now use this Substack. And I'm thinking about of extending the use of Substack, maybe also hosting this meeting like we have today via Substack. But my literacy with this Substack is still its infancy, so I don't know really how to do it well. So that's why we stick to Zoom for the time being. Okay, what else did I want to say? I guess that's about it. So that's the main change. We now use Substack for organizing this affiliate program of our machine learning group. Okay, so today I want to talk about uh, one of our current research focus, which is on federated learning implementations of all kinds of basic machine learning models and methods. So one of the one of the main methods or main flavors of machine learning is clustering. So now we are busy with trying to make all kinds of basic clustering methods like k-means federated. So I've already posted here or uploaded a first preprint to our archive, and there will be soon coming a new version or a revision. And yeah, this is really work in progress. So I also like to use this opportunity to get your input and to get nice discussions within these affiliate meetups to develop our work further and also to see possible applications. Okay, so let me now share my whiteboard. So I want to start with a short whiteboard talk where I sketch the basic ideas, and then at the later point I will hand over to some of our group members who are conducting numerical experiments, who are implementing these methods that I will now briefly sketch or try to motivate from basic principles. Okay. Yeah, so the basic setting is we have a data set. As always in machine learning, it's about processing data. And so these data points, they are characterized by a feature vector. So this here is characterized by a feature vector of length d for dimension. And our current work is mainly theoretical, so we don't really have a specific application in mind. But there are of course tons of useful applications for these federated clustering techniques. For example, in healthcare, where these data points are patients. So each data point here is one patient, for example, me, and I generate a lot of features, measurements, blood measurements, diagnosis of doctors. So my healthcare record provides a feature vector. So this feature vector X here is basically the hard information in my healthcare records. And often we would like to find groups of patients who behave similar. So in medicine, we are still not there where you have a totally personalized healthcare. So we need larger groups or cohorts. And one way to find those groups of patients is via clustering. So you want to, based on the features of a data point, you want to find a group or a cluster of patients which are more similar than others. So here, for example, we could have two groups or two clusters, and there are different ways to represent the cluster. So if you remember, maybe some of you have have had a basic course on machine learning already. So you can represent a cluster, for example, by just listing all the data points that belong to that cluster. So this is the approach. So this would be cluster one. Let's denote it by calligraphic C1. And we could now list all the data points that we currently assign to cluster one. Another representation is possible if we have numeric feature vectors, which is a cluster centroid. So we could define here the cluster centroid as the average of all feature vectors that belong to this cluster. And then maybe we normalize. Yeah, we normalize by the current number of data points in this cluster. And we have the same for the other cluster, cluster 2. Yes. But there are also other ways to represent clusters. Today we will focus on this maybe most direct way to represent a cluster, which is by a list of data points that we assign to the cluster. And equivalently, or once we know all the data points that are in this cluster one, we can immediately compute the cluster centroid. So we can also equally a full characterization of this. It's called hard clustering because each data point is in one and exactly one cluster. This can be characterized or parameterized by the cluster centroids. Yeah, by the way, just to make a bit of advertisement for our Alto dictionary. So all these terms that I use here, if you want to read more about them, in the sense that I use them, please check out our Alto dictionary of machine learning. If you Google it or search for it, you might find our GitHub repository. So this is currently on GitHub open source, the Alto dictionary of machine learning. And there you find, for example, what exactly I mean by cluster centroid, but now I have explained it here actually pretty precisely. So it's the average of all feature vectors, of all the feature vectors of the data points that belong to the same cluster. Okay, so one basic flavor of clustering, which is called hard clustering, amounts to finding a partition. So we partition the data points into a given number of clusters. So this number of clusters partition data into a given number k, we call this k, clusters. And each possible partitioning, so here I show one. Here you see one possible partitioning of the data set into two clusters. So this would be an example here for k equal to two clusters. Is parameterized by the cluster centroids. So we have the first cluster centroid up to the kth cluster centroid. And this, in a sense, these are the model parameters. So these here are model parameters for k-means for this hard clustering model. And then, of course, we need some way to measure the quality of a specific choice of model parameters. So how good is this particular choice that I drawn here of model parameters? Well, in clustering or in this hard clustering setting, one natural choice of quality or loss. So in machine learning, we always need a loss function that tells us how good a certain choice of parameters is. A natural choice is this average distance between the cluster centroid and the data points. So in some sense, we measure the spread across a cluster. And we want the cluster, of course, to have a small spread. So we can define the clustering error by using L, which is intentionally because it's a loss function. So we use the clustering error, or we define the clustering error loss as a function of the cluster centroids as the average Euclidean, or let's be precise, squared Euclidean distance to the nearest cluster centroid. Okay. So what hard clustering methods do is they are a form of empirical risk minimization. So they minimize the loss function, they minimize this clustering error, and yeah, it will be handy to stack those cluster centroids into a single matrix W. So we just stack those cluster centroids into a matrix just for the sake of easy notation. And so what clustering methods do is they optimize or they minimize this loss function, this clustering error. So this matrix is of shape. We have the columns are the cluster centroids. So the number of rows is any guesses from the audience who are allowed to speak? Yeah, I must say that I'm very restrictive in these open meetings for the time being because they are fully open. So I share the Zoom link. So I only grant the right to speak only to few in the audience, typically co-speakers. So anybody who can speak, do you have guesses what the shape is of this matrix W? How many rows does W have?
N.
K.
K, N, K, yeah. So K at least is so far used by me. What other symbol did I use for dimension?
D.
D, yes, D. Very good, very good. D times K. So we have K, so this matrix here has K columns, and each column is a vector of length D. Okay, so this is clustering. Clustering methods are an instance or a special case of empirical risk minimization, where the empirical risk is the clustering error. Okay, what is a challenge here? A challenge here is that in contrast to other empirical risk minimization methods like regression or yeah, regression using linear models or using deep learning, uh, this function here, L of W, is typically non-smooth. Non-smooth and non-convex. So it's among the hardest objective functions you can think of. And this rules out, in general, basic use of gradient descent. So what sets these clustering methods apart from linear regression or from regression using deep neural networks is it's not so straightforward to use gradient methods or stochastic gradient descent. There are works that drill up gradient methods for this solving this non-smooth problem, but it's not so obvious or not so natural as for linear regression, for example. So we use another method for minimizing this clustering error. Does anyone know an algorithm or a widely used algorithm for this solving this optimization problem? So this is in general NP hard if you want to be a bit more fancy in the characterization of the difficulty in general. So NP hard for those who like complexity theory. In practice, still we do clustering. So we use a simple alternative method or a simple iterative method, which is known as Lloyd's algorithm. And again, you find a nice bit-sized description of Lloyd's algorithm in our dictionary. I just briefly give the main idea. It's instead of directly optimizing this clustering error in terms of cluster centroids, we also use the cluster assignments. We introduce new variables as which are the cluster assignments. So for each data point, we have a variable C. Let's say this is the data point. What do we use as sample index? R is 1. This is the first data point. And then we have a variable here, C superscript R, which is the cluster index of the cluster to which we assign this first data point at the moment. And this is at the moment 2. So it's cluster 2. Okay. And so this Lloyd's algorithm alternates between cluster assignments for given cluster centroids. So somebody gives you cluster centroids like I did in the beginning. I gave you the cluster centroids. I somehow cooked it up myself. Then I can find the nearest, for each data point, the nearest cluster centroid. So I can do this cluster assignment step. And then once we have new cluster assignments, we update the cluster centroids. Okay. So this is, I guess, for many of you, a review of basic k-means clustering. And now the question is, how do we do this? So this is really this is a bread and butter method or bread and butter technique, k-means clustering. Uh, this is widely used in machine learning and data science. The new twist here, or the new challenge in federated learning, is how do we do this if the data points are not at a single location, so they are distributed over several devices. So these data points, they might be, as I said, they might be part of a patient database in a hospital, and it's very difficult. So this might be a hospital, let's say in Helsinki, and this is a hospital in Vienna. And then it's not so straightforward. So I guess those of you who work in healthcare, uh, they can agree that it's really a nightmare to get access to data. So you need to fill out a research permit, or you need to apply for research permits, etc., etc. So the hardest part in doing k-means clustering in practice is to get access to the data set. It's not the nitty-gritty details of this optimization problem or optimization methods. Often it might be the hardest part is to get access to this data point, to this data set. So we are now interested in our current work. How can we make this federated? So how can we design federated clustering methods? And since I worked a lot on total variation minimization or generalized total variation minimization, our idea is to use this technique of generalized total variation minimization. So I will now give a brief overview of this GTV-min. So this is abbreviated as GTV-min, generalized total variation minimization. And the idea is as follows. So let's say you have you have several. I normally use devices or nodes, but now for the sake of this application with healthcare providers. Let's say we have hospitals or some buildings with healthcare providers who collect patient data, and we index by I these nodes. So here we have node I and node I prime here. And each one of those, let's say they could be general practitioners, has their own local database of patients. So, and they want to somehow, for some reason, they want to cluster them. So they want to find out, do I have two or three rather coherent groups that might be prone to getting some flu soon? And then you might send them a reminder, please take a vaccine or something else. And so each one of them could run a clustering algorithm that tries to solve this clustering problem. So we have now a matrix for each of these providers. So we have the loss function is now different for each of these healthcare providers and the optimization variable. So we have now one of these clustering problems at node I and another one at node I prime. So each one of those does a clustering, runs a clustering algorithm, for example, using their scikit-learn implementation or scikit-learn distribution on their Python installation. So instead of having one single of this clustering problem, each one of these healthcare providers does a separate one, a local one. I mean, this is the naive solution. So everyone does their own machine learning algorithm, and I guess this is done currently mostly because people are who are not willing. So let's say you are a healthcare researcher or in bioinformatics, you are not willing to take this pain of getting a research permit accepted and the data access approved, which is really a horror, the bureaucracy sometimes, which is of course also good because it means our healthcare data is protected to some extent. So you could just do, okay, then I use my own local data set. Everybody does their own local machine learning analysis. However, in general, it helps if you have more data. If you're not only using your local hospital in Austria or your local database at a small general practitioner in Austria, but let's say you connect now all the general practitioners across Europe. So you have, in some sense, a common health data space or health AI space. So how can we do this in a way that can guarantee some level of privacy protection? And one way to do this is via a mathematical technique called total variation minimization, or I call it generalized total variation minimization. And the idea is as follows. Instead of solving this single clustering problem using all data, we couple this individual clustering problems by constraints. So we say the clustering between that we get from those two should be identical. So we want to have identical clustering. So how could we do it? Well, a most straightforward way would be, well, if the clustering is parameterized by this matrix here, so we have here a nice matrix of shape D times K, and we have here another matrix. This is the optimization variable at I prime is D times K. So nice numeric matrices, so we can measure distances. We could measure Wi minus Wi prime, and then use some matrix norm, like Frobenius norm or whatever matrix norm you like. And we can force this to be zero. So the optimization variables should be identical. So they should be in consensus. There should be a consensus among the optimization problems, the individual optimization problems. What could be a problem in this approach? Why could this be not so useful for clustering? Well, a challenge here in this parameterization is that we have some uh, symmetries, or let's say it's not clear that each one of these local k-means algorithm uses the same numbering of clusters. So for the node I, they might use this cluster here as cluster 1 and this cluster here as cluster 2. But for the clustering itself, it doesn't matter in which order you use the cluster centroids. So there's some order invariance, which makes this a bit more tricky. So in particular, if let's say we have the node I has this cluster centroids 0, 1 and 1, 0, and node I prime has a different the reverse order of this cluster centroids. So the matrices are different, but the clustering is the same. So that's why we use a different, so to take care of this special nature of the parameters here, of the model parameters in clustering, we use a different choice for this discrepancy or variation term. So we use a measure that makes sure that the set or the columns, the set of columns in Wi is identical in the sense of sets. So the sets must be identical, must coincide to the set of columns in the clustering at I prime. So the set of columns must be identical. So how do you make sure that two sets are identical? How do you make sure? I guess we have at least one mathematician that I know of is a mathematician in the audience. So how do you make sure that two sets are equal? Well, one way is, at least one way is you first show that one set is a subset of the other, and then the other way around. Then you show that this other set is a subset of the first one. Okay, that's also a nice proof technique. So if you are in the need of proving that two sets are identical, one way to prove this is that you show one set is a subset of the other, and the other the other set is a subset of the first one. Yes, so I just got a comment. So it seems some of you can post on the chat, but unmuting is only possible for the hosts. So I need to still figure out how to optimally control the security level of these meetings because I share the Zoom link, and I once had a very bad experience where I was a bit naive and then got a, how do you call it, a Zoom bombing. That was not very nice. So I want to avoid this. Yes, but so some of you knew this trick to show that two sets are equal. You show that one is a subset of the other, and the other is a subset of the one. And this one we can measure. So this being a subset means that that this sum here must be zero. So we minimize over C prime all the current local centroids. So I'm now going a bit into more mathematical detail. I will share a link to a preprint where you can read in peace all these nitty-gritty details, how you ensure these subset constraints. And it turns out you can write down the subset constraints in more like say numeric math or something that is easier to numerically implement using these minimizations. So I prime C I prime. Okay, and this this requirement of being a subset means you require this to be equal to 0. And now we're getting closer to our final choice for this variation term. So we use as a measure for the variation of clusters at some node I and I prime, we use this quantity. So we sum over all cluster indices, and then we take the minimum of these distances, C prime plus, and then another minimizer, which changes the role of I and I prime. Okay, so it turns out this here is only 0. This quantity is only 0 if and only if this consensus is valid. So if and only if the sets of cluster centroids coincides between those two nodes, I and I prime. Okay, so but it turns out that enforcing this, so working with hard equality constraints, is a bit more challenging. So we do something that is related to Lagrangian duality. So instead of exactly making a constraint that this is 0, we add this constraint function as a penalty term. So we add the constraint function here, function as penalty term to the clustering objective. So, and then we end up with our final optimization problem. So we want to minimize all the local clustering problems. So this here is the clustering problem on method at node I. But we penalize using some penalty term the disagreement of the clusterings at connected nodes. So we sum this. So this term here is the disagreement over an edge that connects node I and node I prime. And now we sum over all edges in a federated learning network. So these are all the edges that are connected, that represent connected devices. And let's introduce the shorthand here, dii prime for this whole term here. So we want to minimize this dii prime over all edges. Yeah, by the way, this is symmetric. So we have a measure between two connected nodes that doesn't depend on the order of the nodes. Okay, and this optimization problem is in terms of all the local clustering variables. So we minimize this jointly over all local cluster centroids at all nodes. So, and this here is an instance of generalized total variation minimization. And what is special for clustering? Well, for clustering, the specific choice for clustering is this, first of all, this penalty term here, or this variation term, which measures the discrepancy between cluster centroids. And another thing that is specific for clustering is the objective function here. As objective function, we use the clustering error. Okay, so that was the pretty straightforward derivation of federated clustering, or federated k-means in particular, if we use here the clustering error that is used in k-means, using as an instance of GTV minimization. But now the hard part starts, because now we have to solve this optimization problem. So k-means itself is already a hard optimization problem, and it doesn't get easier by adding this penalty term here. However, we can use a similar idea as for Lloyd's algorithm to cope with this minimization terms. So this minimization terms make the optimization problem so difficult, roughly speaking. And how do you cope with these minimizers? Well, you try to solve the minimizer step with this current local cluster centroids held fixed, and then you update the local cluster centroids. This is a similar alternating optimization idea as for the basic Lloyd's algorithm. And we use this same idea in now this federated clustering method. And yeah, I will not now jump through this method step by step. I rather would like to ask Salvatore to present some of the numerical results that we got for our method.
Hi. Let's see.
Sorry. We have
Yeah.
first Q. So Q also worked together with Salvatore on this experiment. So please take it over, Q.
Okay. Can you see my screen?
Yes.
Okay. Here I show the experiment we did for this federated k-means using minimization, using GTV minimization. First of all, we generate 3 synthetic data sets, and each synthetic data set contains 3 clusters in 2 dimensions. The first data set, we name it blobs. We implement it by using scikit-learn blobs benchmark. And the first row here are the blobs dataset. The clusters are well separated and they have very good Gaussian shapes. And the second dataset, we call it Aniso, which is a variant of this blobs dataset. The second row, the clusters are reshaped after a linear transformation. And the third dataset, we call it varied, which is also a variant of the blobs dataset. Here, clusters have different variances. After that, we randomly split each dataset into multiple nodes or devices. For communication graph, we construct an ER graph with a given edge probability P. In this way, we can simulate the communication between nodes. So when P equals to 0, we have a graph without any edges. And when P equals to 1, we have a fully connected graph. And then in this single experiment, we run number of nodes equals to 3, number of samples, which is the number of total local data points, equals to 1000. Then we set P equals to 0.8. So we have a well-connected graph. And we run it for 100 iterations, and the regularization parameter alpha in our algorithm is set to 1. And here we get the results. For this first row, on blobs dataset, each subplot represents the results from one node. So node 1, node I, and node 2. And we get the final round of centroids from 3 methods. Red cross, which is central k-means. We run k-means on pooled dataset. And the yellow dot is our method. The green star is local k-means, which is each device runs k-means independently without any communication. So here are the results. We can see first row for this data set. Visually, those centroids are quite closer to each other. That's because we got sufficient data points and the structure of the cluster is quite simple. But is our consensus term working? We can check it from the table. For dataset blobs, different algorithms, ours and local, and this error central is our evaluation matrix, which is basically the mean squared distance between of local centroids and central solution. So this value is smaller than this value, which means that our method derives centroids closer to the central solution. And that answered the question. Our consensus term is working. Let's check the second row, ANISO dataset on 3 devices. Similarly, we get the final round of centroids from different methods. Here we can already see that in this cluster on node 0, our centroids is closer to the central solution than local k-means. Same here. And let's verify it in the table. Dataset ANISO, and this value is smaller than this value, which verifies the result. And let's check the last dataset, varied. We can already see that on node 0, on this purple cluster, our method yellow dot is closer to the red cross than green. And same here. Let's check the table on varied dataset. Our algorithm have a smaller central error than local k-means. Okay, so this is the results from this simple experiment. For the rest of the experiment, I will ask my colleague, Salvatore, to take over.
Okay. Can we please? Hi. So after doing the experiment just one time, we redo the same with different values for the connectivity of the Erdős-Rényi graph and for varying local sample size for every device in the dataset. So we redo for every value of the parameter the experiment 10 times, and these are the results. So for the cluster blobs, these are the results in terms of central error, so the difference between the cluster from the JTB mean and the central federated k-mean as baseline. And as you can see, with the increasing of P connectivity and local the dataset size, the R central decreases, which means the performances improves. Same thing happens for the type of cluster ANISO, and the same with varied, with different values for the performances, but the behavior is the same. So we plotted also the between node variation, so the difference between the cluster for in between devices, in between nodes, and also with the increasing of P connectivity and dataset size, we can see that the performances increase in the sense that the error decreases. Same thing with ANISO, and finally with varied. Then we wanted to show the effectivity of alpha. So again, we repeated the experiment 10 times, varying the alpha of the regularization term between 0.1, 0.5, and 1, having the connectivity of the graph fixed to 0.6. So here are the results for blobs, in which you can see how the increasing of alpha greatly increase the performances. And same thing with aniso. And lastly, with varied, also with the same behavior, in which increasing also the local dataset size increase the performances of the method. Okay.